welcome to yet another Focus Chat. I'm Alex Bolboaca and I'm coming to you from the Mozaic Works studios once again. The topic for today is resilience testing and discussing about resilience of software systems, particularly about their relationship with business. And as usual, my guest today is Adi. Welcome, Adi.
Hello, nice to be here again.
So before we go into the actual topic, what have you done lately? Anything new, interesting?
Yeah, of course, there are always interesting things. I cannot say much about this, but I am helping a few organizations on let's say, becoming more able to adjust constantly to the market and be able to deliver value in a constant way to the market cadence. So in this endeavor at one of the organizations, I had this we have this need to look at resilience. And yeah, because it's a complex setup, there are a lot of moving parts, a complex system where we touch a lot of the existing areas of the whole organization, at least from the software point of view. And this is one of the important aspects.
So let's discuss a bit about resilience and what you mean by it, because I've noticed whenever I discuss with architects, whenever I discuss with technical people, they look at me very puzzled when I talk about resilience, when I talk about systems that should stay up, basically no matter what happens to them. That would be the ideal.
Yes.
We are far from the ideal, but that would be the ideal. So what would be your definition or your description of such a system?
So if we go very far away to say the perfect, let's start from the perfect system. The perfect system in resilience means self-healing systems. A system where if something fails, the user will not observe any failure, because somewhere in its insides, the system will have some sort of getting back to a normal or at least partially normal state, and the user wouldn't see it, or in this way you wouldn't see an error or wouldn't see a crashed page, but also wouldn't need to wait a long time for an answer to do whatever the user needs to do. So that's the perfect approach. The least, let's say not that perfect approach, is at least let the user do what they need to do, even if it takes a longer time, even if it has some UX user experience issues like waiting more, but still you will be able to do something that you need to do.
And this, whatever happens within the internals of the system. So, for example, if you have a system that runs, I don't know, 100 different servers, plus 1,000 different services that run somewhere. If you have, let's say, 10 of these servers go down, the user would not notice anything except for perhaps a bit of a slowdown.
Yes.
Yeah.
And you can even be nice and say where experience difficulties, it will be a bit slower now. So you can show that. So you can go also on this part.
Yeah. So when things go slow, the user would get a message. Our systems are a bit slow now. Please bear with us, or something like that.
Yes.
So this includes some kind of self-monitoring,
Definitely.
Yes.
You do need self-monitoring for two reasons. One, to give these types of messages to the users, and second, to be able to have this self-healing mechanism, where if something goes wrong, you should have a procedure to follow, automatic procedure, I mean, to follow, and do that, like spawn another system, create another virtual server, I don't know, something like that.
Okay, so before we go into the more technical aspects, why is this important for a business?
Well, in our situation, the users will need to know that what they are doing is predictable. Otherwise, the users will basically create loss of money for the business, because what they do means money, and if any of the data that they are filling, or the information that they are using is too slow, it could mean a loss of money, but also a loss of prestige to that organization. And that is very important nowadays, because especially, so okay, let's say with the people who were born in the 60s or 70s or 50s, so they are in a way used to things being slower. But people who were born in 90s or 2000s, already they expect everything to happen very fast. And there are these studies showing that if users from this age, at least at least most of the users from this age will see such a page where something goes wrong, they will never get back to that system. So that's huge. It means that if once something goes wrong, you'd lose that client for good. And it's in a way a new thing.
So traditionally, this was very important for things like financial services, telecommunication. You don't want your call to be dropped because a server stopped, or because I don't know, some kind of antenna went boom somewhere. You want everything to work, right? For things like probably real time, introducing information in some corporate systems, this would also be, let's say, prime candidate. But what you are saying is that nowadays most users have an expectation that things work and that they work all the time. We don't have patience anymore. We want things to work. We want things to work fast. And we don't care anymore about, companies telling us, but software is complicated. And
no more excuses. That's the idea.
Yeah. So we have fewer and fewer excuses when producing software. Or let's say we stopped having patience from our users.
Exactly. Yeah, that's the idea.
Okay, so obviously businesses care about this because the user experience is also the prime indicator of how business is working and how it will grow. Because if users are happy with, or at least not necessarily happy, but at least neutral, they won't go on forums and social media and bash the services. Right.
Or but even you'd like the opposite, like saying, look, this is a great thing, or a great system, you should try it as well. That's what you need.
Yeah. So if you want the business to grow, one of the prime, it's not the only indicator, but one of the prime indicators is actually how customers see you, the customer experience. So within this context, let's go to the other side of this, which is the technical side. We are talking about complex projects. We are talking about complex infrastructures.
Yes.
So this could run payloads in the cloud. It could run payloads in a hybrid cloud, part of it, let's say AWS or Google Cloud or any kind of provider. Part of it can be within a data center of the organization. You can have some infrastructure that is not in the cloud, is the traditional kind of infrastructure, because not everything has been migrated, and not everything perhaps will be migrated.
Exactly.
You can have thousands of services. You can have hundreds or thousands of servers, all kind of other equipment. I'm thinking about, if you are talking about telecom organizations, they also have special equipments, and not only. So you have this complex infrastructure, right? So now the question is, how can you get to resilience when you are in this context?
Yeah, things are very difficult to tackle, and you need to take it from one side. But the difficulty in this situation is that, so let's say you have this big system that interfaces with other 80 or 90 systems in an organization, and this organization has these systems and has had them for a while. So what you can do, you cannot really say that, okay, I'll have my system, which is customer centric, really well made, and I don't care about the rest. Because quite often it happened that one very small system nobody cared about was damaged during an upgrade and everything crashed. So the difficulty here is that it's a huge system and you need to understand each bit of it, which is almost impossible. So then the opposite is what we learned. I think Netflix started from this with the chaos testing and chaos monkey and so on, where you put your system in a laboratory environment in some sort of cloud or internal cloud, and you start crashing systems on purpose. So you have that small system nobody cares about, and you just decouple it from the rest and see what happens. You monitor everything, so monitoring is essential when doing that, and yeah, you see what happens, you see how it crashes, and then you take measures. Okay, so if that system crashed, let's see what we can do. Let's try to make it work in I don't know which way, and so on. So you do like this with every such system. And I think that's the first thing, trying to understand what's going on from like an analyst, system analyst, or like an architect. I don't think it works with this type of very complex and old systems.
And this relates to the complexity domain of the Kinevin framework.
Yes.
So I won't go into many details about this because it's quite a complex topic, but the fundamental idea is that there is a type of problems for which the relation between cause and effect is not, you cannot deduce it. You cannot find the relation between a cause and effect. So let me give you an example. When you have such a very complex system, as you said, perhaps today it goes, or part of it goes down because server 1 failed, right? And you go and you fix server 1 and you introduce some measures to prevent server 1 from failing. Perhaps you had some redundancy and so on. This doesn't prevent the system tomorrow from breaking in exactly the same place, but due to something else. There's no relation between cause and effect. You can have the same effect caused by different things, or you can have the same cause causing different effects. And because of this, what we are saying within the complex domain is you don't have a relationship between cause and effect. And if you are working within such a domain, then what options do you have? You cannot analyze and figure out what will go wrong, right? Because there's no relation between cause and effect. The only thing you can do is to experiment. And fundamentally, this is what Netflix has done. What they said is, we have this complex system, we want it to work no matter what happens to it, so let's experiment with it. And they introduced the Simian Army, which is on different levels. So they have the Chaos Monkey, which is going and shutting down servers or services, and it randomly shuts them down, even in production, right? But they make them sure to look at the monitoring and to make sure that the system still works. And if something doesn't work, then they know they have a problem and they need to fix that. They have the Simian Gorilla, I think, which shuts down full areas. So, for example, they will shut down everything within the AWS area from US East 1 or something like that, all their systems. And you as a user, you shouldn't feel anything. You should still be able to continue streaming. You should still see your lists, see the movies, watch if you are watching anything. Just immediately, continue streaming from another area, as simple as that. And I think they also have another one, which I don't remember precisely what it's doing, but fundamentally also shutting down other things from the system. So, and the problem with this approach is that it's so counterintuitive that when I talk to many architects about it, they look at me like I'm crazy. It sounds weird, and it is weird, but it is weird because of the nature of systems that we are working with. If we are working within the context of complex systems, automatically you don't have this cause and effect relationship. So your only option is to go and experiment and try to figure out how to what doesn't work, instead of analyzing everything and figuring out what might not work. You proactively try to break things so that you find out what doesn't work.
Yeah, I think it's also a matter of looking at how things break, because typically programmers and architects have this tendency to believe that what they do will function, while testers and maybe engineers operations engineers or DevOps see that things fail, see them in their own hands. Testers try to make system fails, and especially operations engineer who work on production, they see them fail. So I think there's this mismatch in a way on experiences. In a way, if you're an architect and you have never seen or worked on production site or on production environments, it's very difficult to understand that any of your system will fail, and it's very difficult in a way to accept that, because it's like your baby. But that's where you need to start from. Everything will fail at one moment, and you just need to understand what you need to do when it will fail.
Yeah, one of my favorite definitions for software architecture, which is, so software architecture is fundamentally difficult, I'll say quasi impossible to define. But one of the definitions that I think puts a light on this type of thinking is the idea that software architecture is when code meets the real world. You take your code, and your code works on your computer. Maybe it works on two computers within the development environment. But then you take it and place it on a server in the real world, and then things start to happen to it. Hard drives fail, network cards stop working, networks go down, changes in the operating system make your code not work as well anymore. The hard drives are full. There's a sun eclipse, and something bad happens to, or actually, you can have things like sun storms, radiation that goes and fries some of the magnetic equipment that you have, and so on. Plus, you have actors who are actively trying to break your system.
Yeah.
Right. So you have all these things that can happen to your code, and none of that is good, right? It's like they say with cars, that once you take the car out of the dealer, only bad things can happen to it. It's
of course,
right. So the same happens with code, and my feeling working with architects in our learning programs and helping architects improve the architecture of products is that not all of them realize the extent of this, how much and in how many ways your system can fail. And in a way, it's disheartening, right? As you said, because I'd like my system to work. I'm putting certain tiers to making it work and so on. But then it goes into the real world, and only bad things will happen to it. It's as simple as that.
A very interesting aspect is that when you start seeing that working in this way and seeing how things can crash, you will understand, in fact, the importance of looking at complexity as well. Because, okay, you've done, let's say, load testing or performance testing. So you just put 1,000, 2,000, a million users, and at one moment you'll see your system crash. That's this type of load testing, and that's fine. Okay, it shows you where the system works. But this is just, let's say, a simple type of test, because in real life, what can happen is that you'll have not that many users, maybe half of the maximum that you can, but another system will have 95% the database, and another system will have 95% of memory usage, and something very weird will happen. So in complex domains where we're talking about with 50, 60, 70 systems running, that's where problems start appearing, and it's very, very difficult to predict that. And I think that's why it's important to look at complexity. And in a way, I guess it's also the current, let's say, modern approach of software, where you have more systems rather than what you had in the future, the monolith. With a monolith, maybe it was rather easier to tackle this because it was easier to look at. Of course, you couldn't work your way through running it with more servers or with more users and having this dynamic approach to have to increase the capacity of the system and so on. But I think it's also a problem of going out of the monolith era, and this is why this happens.
Yeah, still distributed systems are not new. They have been around for a long time. But I still feel that many people don't understand that distributed systems are a completely different beast from monolith or from single server systems. So even from simple scaling, like the vertical scaling, when you have the same application running on 10 servers, that's still easy. But when you talk about distributed systems, one of the consequences is that when the number of systems increases, with the number of elements within the distributed system increases, you are entering the complex domain. Another thing that happens is that you start dealing with the cap theorem, which fundamentally says that once you have multiple databases in your system, you need to go with eventual consistency. You cannot have consistent data on all the databases that you have at the same time. You can reach consistency, but only eventually at some point. And this is an unexpected effect. If you've never done distributed systems, you don't think about this. But beyond that, I think, well, it might be interesting to discuss about how you know that your system is improving its resilience.
Yeah.
Right? Because we have discussed about some of the technical aspects and the mindset of figuring out how to deal with this and how to discover these problems. But how do you know you are improving?
I guess, of course, you could look at it from the user's point of view. Less complaints is better, or less reports. But I guess the most important thing is to have a real solid monitoring system on production and look at that. Look at how you are behaving. To go really technical, if you look at resilience, it's a ratio between the mean time to failure and the mean time to recovery. So if you're measuring the number of failures and their duration, and then you're measuring for each one of those failures how fast you succeeded to recover, then there you go. This is your metric. I guess with a lot of high quality monitoring you can do that, but also I think you can see in your laboratory environment, as I said, where you want to crash your system, you can test that as well, so you can evaluate it there. If you keep crashing systems and still your whole system will be able to resist and continue to work, that's another good measurement to see that you have increased resilience.
Right, so let's go back a bit to these indicators. So mean time to failure means, let's say you have in a year 20 failures. Okay?
Yes.
So this would mean that what you are doing, you take the time between two failures and you compute the mean value for that, right?
Yes.
So for example, if you have a failure every 2 weeks, then 2 weeks is your mean time to failure.
Yes.
Of course, you won't have them neatly structured like this.
Yeah.
Perhaps you'll have 1 in January and 10 in March and 200 in, well, hopefully not, in September, and none in the other months, but you still look at the time between them and you get them in time to failure. And this is important because it shows how often you can expect to have a failure, right? This is the idea. Mean time to recovery, on the other hand, is once you had a failure, how long does it take you to recover from that failure?
Yes.
And you can imagine that if you need manual intervention,
it will take a long time.
Obviously, it will take longer. If you have some automated systems like self-monitoring, for example, something is monitoring a server. If the server goes down, restarts it, or starts another server and reroutes all the requests to the new server. If you have such systems, then you can expect smaller time to recovery.
Yes.
However, even with these automated systems, you can get into trouble with due to the complexity aspects. So it can happen that your server gets a lot of requests, goes down from some weird reason. Those requests then pile up into another part of the system. You restart the server in the meantime. Some of the requests go there, but then they pile up into another area, and that area goes down. So you can get this thing like cascading failures. You can get, even with automated systems, right? So it can even go down like this. So that's the challenge of this complex infrastructure and working within the complexity domain, that you have not only one failure, but once something fails, then you can get a cascade of failures that compound. So it's not enough to just look at every system by itself, but you also need to look at the systemic effects of systems going wrong one after another.
Yes.
This reminds me of a funny story with Slashdot.org, which managed at some point to apply denial of service attack to themselves, because they changed something in the network infrastructure and they started sending some network requests that were repeated within the network and amplified, and they managed to bring the whole network down by themselves by doing this. It was a very interesting post-mortem back then. So that's one example of something that can happen.
Yes, of course, but because it's complex domain, you can have like a situation very common would be if you don't treat it right. Let's say that you, in fact, something crashes, you put it in a queue, and then your retry strategy has its interval is very short. So that what happens is that you have, instead of having, let's say, one node, you have 5 nodes, you have just one node working, and because you retry so much, you even put that node down, because you have a retry strategy which is in fact doing what you said, something like a denial of service, but you do it on yourself. So there are these things that need to be looked at in the whole ecosystem. You cannot say just like, okay, we've done a retry strategy and that's fine, it will work. You need to understand how and what could be the effect. Sometimes it's better not to do anything than to try to do something from this point of view. So just wait until the system works and put that thing that we're slow now, we're going slow now, putting a message to the users.
And this brings us to an interesting point, which is there are some things that you can do within the architecture and actually even within writing your code that help with resilience. They don't fully solve the problem of resilience, but they do help. And one of them is the one that you mentioned. So you can use message queues that have retries, and you test them for retries, for a specific retry policy and so on. Another one is the safety, so what it's called. There are systems that you can use. There are libraries that you can use. Let's say you want to call an external API or an internal API, right? And you call, instead of calling directly, you call through these libraries. And those libraries, you also set them up to retry or to with a retry policy or with specific types of calls. I don't recall precisely the name of the technique, but this is one option. Because otherwise you'd have to write your own retry code, which is is complex.
Yeah, it
once
is.
again.
It is complex, and I think it should adapt to the context. That's even more difficult. So it should look at many aspects and adapt to the context. Probably a progressive and digressive, maybe it's better. Retry policy is a lot better than trying to call every 5 seconds, call back. It's better to see it's not working, let's try in 10 seconds. It's not working, let's try in 20 seconds.
Yeah,
because otherwise you really can put systems down.
Another thing that you need to have in your architecture, and in this case in your infrastructure, would be monitoring. Load balancers obviously help within this context. Monitoring, you need to pay attention to what you are monitoring, because some of the things are memory hogs, some payloads are disk heavy, some payloads are CPU heavy, and if you have them separated, at least you can have an idea of what might go wrong. So for example, if you're doing, I don't know, video processing or things like that, you expect CPU heavy stuff. In that case, if your CPU goes to 99%, it's probably a good time to start another instance. That would be an example. But if you compound these services together and you run them on the same server, then the monitoring might not tell you the whole story, or might not give you enough or granular enough information so that you can actually react to what is happening. What else can you do? You can, of course, have additional code that deals with, that responds to monitoring events. So this is something that is more complicated, and you have to be very careful with it, because as we said, you work in complexity domain, some of this code might have unexpected effects. But you could, for example, if you see something happening with a server, you could also have some code that does something else to the infrastructure and deals with it. I think that's about it. These are, let's say, the main tools that you can use. Of course, there are some attempts of using AI.
Yes.
For this, which makes sense because you might find some patterns in your infrastructure, particularly depending on the number of users, number of requests. So maybe during the night you have less calls, or the other way around, during the night you have more. So you could train an AI system, a machine learning system, to make decisions based on what is going on within your context. But again, be prepared, because these things can go wrong. It's not 100%.
Yeah, and with AI, I think you introduce even more complexity. So sometimes weird things could happen that you couldn't ever expected. So it can help probably in most cases, but in some limit cases, probably it's worse.
All right. So to recap, it's more and more, resilience is more and more a business problem, because we want our systems to work. We want our systems to work fast. We don't want to wait. We are not patient anymore with software. And software needs to adapt to the users and not the other way around. Second, look at mean time to failure, mean time to recovery. This is something you can quite easily measure. Even if you don't have some automated systems, you can get a rough estimation by writing down some numbers in Excel, right? When it starts, when it ends, you can compute these things. Unless you have thousands of problems in each case, you start by fixing them and then you measure. We mentioned the mindset of architects, which is very useful. Switch your mindset to the idea that things will fail, particularly within distributed systems, particularly within complex systems. You can use the cloud, you can use load balancers, you can use monitoring, you can use these types of software libraries to improve resilience. And I think this about covers it. Anything else you can think about?
No, I think we covered a lot of ground, and it's really important when you have a complex system to look at this. I think it's something that will probably make a good product, a difference between a good product and a great product, even now, but in the near future, it will be essential.
All right. Thank you, Adi, for this topic.
Thank you.
And for the chat. Thank you everyone for watching us. I hope you enjoyed this. As usual, we have to pay our dues to the YouTube algorithm, so please like, share, subscribe, tell other people about this. Perhaps show it to your colleagues, programmers and architects and business people who may want to know how to deal with these issues within the context of their business. We will continue recording these focus chats. We also have a few more guests on the pipeline for our conversations stream. So I hope you will enjoy this channel continuing from this. Thank you so much for watching, and until next time, remember to think, design, and work smart.